function itself in the denominator and its derivative in the numerator. So for example, let's see here, this will go back a couple spots for us. If we had something like the natural log of x squared minus 5 that we're going to take the derivative of. Okay? Just as a quick reminder, what you would wind up with is a derivative, and it really is just as straightforward. You take whatever's inside of the argument, it's inside, put it in the denominator, and then the derivative of that goes in the numerator. And you're done. That's the derivative. That's all there is to computing derivatives of natural logs. The biggest difficulty that can come into play is if the stuff inside winds up being messy. Okay? Or you have to take the derivative of the stuff inside. That goes in the numerator. Otherwise, derivatives with natural logs are pretty straightforward stuff. Okay? Where we had left off the other day was with an example here where we're looking at an experiment where we give people a sheet paper and it's got a bunch of nonsense syllables on it. Nonsense being 3-letter combinations. And ask them to memorize a bunch of them. And then come back a minute later and, okay, what was on the list? Come back 2 minutes later, what was on the list? And see what percent of the people can at 1, 2, 3, 4, 5, 6 minutes get the list correct. So it's studying retention, short-term retention of information. And the model that we're given for this is listed over here. And one of the things I mentioned the other day is it's very important when you're given a model that's describing something that's going on to pay attention to the domain. The domain, I know in some cases where just, well, what's the domain of this? Well, it's just some numbers and blah, blah, and you move on. That is not the case when you're working with an actual model. Okay? Those domains are important. They mean something. In this case, could we start at times 0 to see what the retention rate is? No. We can't start any lower than 1. And we could take a look at this. And if we tried to evaluate this function at 0, we're going to have 80 minus 27 times the natural log of 0. What's the problem with that? Natural log of 0 is undefined. Okay, natural log of 0 does not exist, so there is no value that exists at that point. And in this situation, it makes sense. Because at 0 minutes, how much can you really remember before you've seen it? Oh man, don't you have great memories from tomorrow? It hasn't happened yet. There's nothing to remember, right? Well, that's times 0. Okay? R gives the percent who retained the symbols. Or the, I'll just leave it at that. Now, if we do something like R of 1, let's understand what this thing's given us. R of 1 is going to be 80 minus 27 times the natural log of 1. This is fairly straightforward to do because what is the value of natural log of 1? 0. So that means we're going to have 27 times 0, and this is going to work out to be 80. Now here's where things get a little bit tricky. What's 80 mean? Okay, that's close. After 1 minute, 80% of the people will remember the list of syllables. Okay, so what this retention is the percent of people who remember the syllables. Does that make sense to everybody? Okay. Now, where things can get a little bit trickier is, so we did that, got that done. Second thing we're going to look at here is we're going to compute the derivative and evaluate it at 2. Well, computing the derivative itself is not a horrible thing to do because, remember, our original function is 80 minus minus 27 times the natural log of t, and with the derivative being respect to t, the 80 is going to be 0, isn't it? When you take the derivative, you're going to get r prime of t is a negative 27. And then what's the derivative of natural log of t? 1 over t. So it's going to be a negative 27 times 1 over t, which is going to give you a negative 27 over t, which is exactly what we have here. Okay, that's the derivative. Part C asks you, okay, evaluate the derivative at 2. Well, that's not too bad. That's going to be a negative 27 over 2, which is going to be a negative 13.5. Okay. And if you check, yep, sure enough, there it is. The derivative evaluated at 2 is this negative 27 over 2, which is negative 13.5. Now, this is a small part of calculus. Getting negative 13.5 is okay, but it's not very useful. If somebody just came up to you and said, the study came up with negative 13.5. Negative 13.5, what's that mean? Putting a meaning to the number in the context of the situation is something we're going to talk about every time we take a derivative or every time we integrate. Because I don't want you to find yourself at P&G or Kroger or wherever, and there's a discussion going on, and something like this comes up, and somebody says, well, gosh, what's that mean? Or you're doing a presentation yourself, and it winds up being negative 13.5, and you try and zip over it real fast because you don't know what it's negative 13.5 of, and somebody says, whoa, wait a minute, Chuck, negative 13.5, what's that mean? What does it mean? Well, remember, this is a derivative, so it's going to be talking about a function or a change in a function. Derivatives are, begins with an S, slopes. Slopes talk about how things are changing. Aha. So this negative 13.5 is telling us how the retention rate is changing at what time? 2 minutes. What that negative 13.5 actually means is, if we look at the number of people who can retain all the syllables at 2 minutes, and then move to 3 minutes, and now look at the number of people who can retain all the syllables, the percent who can still remember the syllables will have decreased by 13.5%. With a derivative, it's important to remember that that number can always be viewed as a fraction over 1. So whatever the starting point is, in this case 2, the derivative tells you how much of things change by the time you get to the next, whatever one more is. And bless you. So this would be from 2 minutes to 3 minutes. So between the second and third minute, 13.5% of the people forget some of the syllables and they're in trouble. Or they're out of the experiment. Does that make sense? So really important that you can understand what these derivatives are. It's certainly not the last time we're going to talk about what does the derivative mean. We're going to keep talking about it all year long. Because by May, I want you to be able to interpret derivatives, not just compute them. Interpret integrals, not just compute them. Because getting a number and having no idea what it means is useless. Okay? So we're going to stay on that all year to make sure that by the time spring rolls around, you're going to be very good at interpreting as well as computing the values. All right, so that's pretty well got things taken care of here in section 2.3. What we're going to dive into now, and this last slide is just a quick reminder that to compute the derivative of a natural log, you just put the derivative of the inside, whatever this is, over the function itself. Are you all good with doing derivatives on those? Everybody's good? Great. Okay, let's dive into section 2.4. And let's see, these slides are posted. So if you ever want to print anything out or whatever, they're available for you to make use of. All right. In section 2.4, we're going to start talking about growth. There are two different types of growth models that we're going to focus on. One is an uninhibited growth. That means it can keep growing and growing and growing. Is there anything on earth that really keeps growing and growing and growing forever? No. Okay? Except death. Okay? And then there's what is limited growth. This is what's happening to Venezuela and what's happened to Greece and places like that. Their debt grew and grew and grew, and then what happens? The country collapses. Okay? Finland collapsed recently because of debt. Did you know that? All three of them have one thing in common with regard to their society. They're all socialists. Okay? You can only tax people so much and you're running out of money. Okay. What we're going to look at is two different types of growth. One's uninhibited. An example of this that you may have at some point studied in a biology class is a growth of a culture of bacteria. For a period of time, that culture's population will grow and grow and grow, and it'll grow at an accelerating rate. Okay? But there comes a point where either there's not enough food, or there are too many toxins and waste building up, or something or rather happens in that environment that the population can no longer be supported, and at some point it crashes. Uninhibited growth on planet Earth at some point hits a brick wall and stops. The second type of growth is what is called limited growth model. This is also called a logistic model. In a logistic model, it grows exponentially for a while and then it levels out. And this point at which it's leveling out is its limit, or in biology, if you're studying animals, it's the carrying capacity. Okay? For example, in blue ash there is a carrying capacity for deer. In other words, there are only so many deer that can live in blue ash. They run out of food, they run out of space. Ronald Reagan starts to thin them out, the highway, not the man. Okay? And you wind up with a population level of whatever it might be. That's all well and good and cute and stuff like that, but Chuck, I'm going into marketing. This stuff with deer doesn't really affect me other than my tulips out in the yard that I'm trying to grow. In marketing, a logistic growth curve is very important. There are a lot of products out there that you only sell one of. For example, you got a DVD of a movie. How many of you go out and buy 7 copies of the same movie? Usually one's enough, isn't it? And ta-da, you're done. Okay? After you've sold the one, you're not going to buy another one. Well, what happens is at some point, everybody who is interested in that particular movie is going to have bought one. L. That's the limit to the total sales. In marketing, the question is, when do you stop advertising that video or movie or whatever you want to call it? And strangely enough, you don't stop advertising after you've sold the last one. You stop advertising at L divided by 2. So if you're anticipating selling 4 million copies of this movie, after you've sold 2 million, you stop. Okay, this is a general rule of thumb in marketing. Well, we've only sold 2 million, we got another 2 million to move. How are we going to sell them if we don't advertise them? You depend on word of mouth at that point. There's enough of the product out there and in the various populations that are going to be interested in that particular product that they're going to start telling friends and things like that, and that gets the other half sold. It's important to know when to stop marketing. Marketing is not cheap. How much does a 30-second ad on TV cost? Yeah, it depends on when it's showing. If it's with reruns of Carol Burnett at 11:30 at night, it's probably not too expensive. But if it's during halftime at the Super Bowl, it's a couple mil for 30 seconds. That's a whole lot of hot dogs you have to sell to make a couple $1 million back just to pay for the commercial. So with marketing, you've got to know when to stop advertising. Because that money that you would be spending in this region here where they're going to sell anyway could be spent on the next project. Okay? That could be the difference between making and breaking whatever the next product is that you're going to market. So we're going to look at two different types of modeling functions. We're going to go with the uninhibited first because it's easier to go with. What winds up happening with these, and when I was first presented these as an undergrad, I looked at that and thought, really, that's a question? That's an equation? That's math? The equation that you have to satisfy is this. What we're trying to solve is dP dt equals K times P. And, when they first put that up there and I saw it for the first time, I thought, really? That's math? What's going on here? And what you have to do is pull this apart a piece at a time. In the numerator, it's talking about the change in the population over the change in time. Okay, so that's what that means. The denominator also tells us the name of the variable. What is the variable in this equation? T. The numerator tells us what is the name of the function we're working with. In this case, it would be P. Now, think about what's going on here. What this says is if we take the function, there it is, P, and we compute its derivative, we're going to get P back. What function do you know of that we can take the derivative and get back what we started with? E to the x. So these are going to work with e to the x. But Chuck, where's this k come from? K is a number, it's a coefficient, and that's going to come from the exponent in the e to the x function. I'll show you here what's going on. Okay? What winds up happening is we're going to start with a derivative and work backward to get the original function. Okay? Please? This will be for the uninhibited growth. Yeah, what we're headed toward is the equation for the uninhibited growth. Now, what winds up happening is there are several different types of notation that you're going to run into. You can either say the derivative equals the function, like on the left-hand side, or here we have the derivative equals the function there. Those are the two most common notations you're going to run into. You need to be familiar with both because you're going to see them in the book, on tests, and wherever else you wind up going. In either case, the solution is going to look like either y equals or f of x equals. And notice that the model itself is going to be c times e to the k x. That's just a bunch of letters. I thought we were doing math. Okay? This is setting up a pattern that will work for any uninhibited model. To make it hopefully a little bit clearer, let's take a look at something like this. What this says is when we take the derivative of a function, we get back the function times 5. So what we want to do is we want to figure out a function named a, and what's the variable we're going to use in this function a? T. Equals. We know that the function that will return itself as the derivative is going to be e to the, not x, but in this case e to the t. And if you look back previously, Do you see up in the exponent it had a coefficient k? There was a number up there. What winds up happening is the number that's up here will appear as the coefficient here. Come on. It'll be that 5 when we take the derivative. The coefficient that we're going to have up in the exponent is actually 5. Now, if you think about it for a second, you can see the pattern and how it fills in. When we take the derivative of e to the 5t, it's a chain rule. You take the derivative of the outside, and you get e to the 5t. Times. Chain rule says the next thing you do is you take the derivative of the inside. In this case, the inside is the exponent. And what's the derivative of the exponent? It's 5. So whatever coefficient you have out front here, that's going to be this coefficient up in the function. Does that make sense? The other thing that we can take a look at here is this 5e to the 5t really is 5a, because a is this whole deal. You can replace that part, and what you're going to get is 5 times a. Once you have that done, if you go back to the original, notice that there is also a constant out front, c. We've got to deal with how to get that. The way that you compute that is by taking things a step further. Right now you've learned how to build the model so that you have c times e to the 5t. We haven't figured out how to compute c yet. That's next up. Okay. Let's see here. This is what we want to go after. Okay. Suppose that you have some amount of money that you're going to invest. Okay. This some amount of money could be your first year's 401k savings. And you want to invest it toward retirement. Okay. You're putting it someplace where it's going to get 7% continuously compounded. And the question is, what does the function p of t look like for this? Well, we can play the game just like we did before. We're going to have p of t equals, we're going to have a c in front. We don't know how to figure that out yet, but we'll see how that works in a minute. We're going to have our e, and up here we're going to have k times, what's the name of this variable? T. The k is defined by whatever this coefficient out front of the function is. So what this will allow us to then do is to modify this to be c e to the 0.07 t. Everybody good so far? What c works out to be is p sub 0. Okay, well that doesn't help much at all. P sub 0 is the initial amount of money. If it's bacteria, it's the initial number of bacteria. If it's deer in blue ash, it's the initial number of deer in blue ash. It's whatever the thing is at the start. And then the e to the kt is going to allow for its growth over time. Does that make sense? If, for example, let's say that the initial amount of money that you have in your 401k is $5,000. The formula to describe its growth, that $5,000 growth, is going to be, well, we're going to have our e to the 0.07 t, and what's going to be this coefficient out front? I'll take a look up here. The coefficient out front is p of 0. And what's P of 0? It's the 5,000. It's the initial amount. It's what we started with. So you would look at, gosh, what are we starting with? 5,000. Okay, that goes out front. Okay, so what does this do? You now have an equation that you've built up from some information. And this will allow you to predict what is going to be the value of this account in 2 years, 10 years, 30 years, however far down the road. How would we figure out what the value is going to be in, let's say, 10 years? Yeah, put in 10 for T. Plug it into your calculator and boom, it'll tell you what that year's savings is worth 10 years down the road. Now the thing with retirement to keep in mind is you're going to have a 5,000 e to the 0.07 t for the first year, aren't you? And you're going to have another one for the second year, and one for the third year, and one for the fourth year. So you got a whole bunch of these going on, don't you? Each of them running a different number of years. And to figure out the total amount in your savings, you would have to add them all up. Next semester, we'll figure out how do you add a whole bunch of stuff up where it's all changing. Okay, that'll be integration. But for right now, I want you to see where this comes from, and you may or you may not have ever seen this. For continuous compounding, the formula is P0 e to the RT, which is exactly what we have there with the 5,000 e to the 0.07 t. The 0.07 is the rate at which interest is coming in. The P0 is the initial amount of money that was involved. Does that make sense? Okay. Now, let's take a look at this last question here. Actually, let's do the last two questions. Let's do parts B and C here. Part B says, suppose $10,000 is invested initially. Let's say, and this could happen to you very easily. Let's say you work at a company. By the end of your second year, you will have about $10,000, or you should have about $10,000 in your 401k. You should have about $10,000 in your retirement. You decide to accept a position at a different company. And when you move to this other company, are you going to leave your retirement stuff over at this company where you're no longer located? I hope not. So what you do is when you get hired over at this other company, you go down to HR and you say, look, I've got a retirement account over there. Here is the number on it. Move it over to here. You do not touch it. What happens if you touch it or take a check from it? You pay taxes to the tune of between 40 and 50%. So if you had $10,000 there, how much is the government going to take in the way of taxes? $5,000 of it. Whoa. You get it back though, right? It's gone. Okay? To whatever it is that it's going to be spent on. But what you do is you have HR move it over, and by the end of the second year, you got 10 grand, and you point over and say, hey, there's 10,000 bucks over there, bring it over here. So that is how you personally could come up with 10,000 bucks in fairly short order. Right now, that looks scary and like, holy mackerel, I'll never have that in my life. Okay, after about 2, maybe 3 years of working, you should have at least that much in your savings toward retirement. And when you move someplace else, you take it with you. Okay. Suppose that $10,000 is invested. So you move to this new company, and you've got your $10,000 moved there. At the end of 1 year with this company, how much is going to be there now? Now, people get tripped up on this. They mess up on this on quizzes and tests and all kinds of stuff, and they say things like $8,000. Brianna's there shaking her head, no, not my money. What's the problem with $8,000 is the answer. It's less. How are you going to feel if you go and say, hey, here's 10,000 bucks, take good care of it, and you come back a year later and, well, we still got 8,000 of it. Not very impressive, is it? Now, I realize it can go down with decreases in the stock market, but over the long run, it should be growing. The question is, at the end of 1 year, about how much money should be there? It should be more than 10,000 bucks, right? So if you get 8,000, you know it's in need of work. Okay? So, in order to answer question B, we can put down that the amount of money that we're going to have at the end of 1 year is going to be the initial amount, that's the 10,000, times E raised to the interest rate times the 1 year it's there. That hopefully is something that you can crank out pretty speedily on your calculator. And I think it works out to be about $10,725. Okay, so when you work this out, you get $10,725. How much money in interest, let me rephrase that, how much interest did that money earn during the year? 725 bucks. What did you have to do to get that $725? Nothing. Just put the money there and let somebody else work. Well, that's pretty cool. Now, here comes a very important question. Part C. If $10,000 is invested, how fast is the balance growing? Because you want this to grow over the next 35 years, don't you? How fast is it growing at t equals 1? Well, if you're talking about growth, you're talking about change. Change, how do we compute change? Derivatives. Okay, it's a slope. Slope talks about how things are changing. So what we're going to need to do to answer part C is to compute the derivative. And P prime of t is going to be our 10,000 times e to the 0.07 t. Now we're going to use the chain rule on that e to the 0.07 t, which means that we're going to multiply by whatever the derivative of the exponent is. And the derivative of the exponent is 0.07. This will clean up a little bit. Well, actually, it cleans up to give you this 700 e to the 0.07 t. Okay, well, if we plug that in, we're going to have 700 times e to the 0.07 times 1, or just e to the 0.07. And what this gives you then is P prime at 1 is equal to 750.76. Okay, so there's the derivative. You figured it out. It's $750.76. But what's that mean? This is the hard part of the class. Yeah, first thing to remember, it's a slope, and a slope is always a fraction, isn't it? It's the change in y over the change in x. So this is over 1. The x values are the year, so over 1 year, this is going to change by $750.76. What this means is, at the end of year 1, as you move to year 2, it's going to increase by $750.76. Notice, as you move from 1 to 2, the amount you get is bigger than when you move from 0 to 1, isn't it? And the reason it's bigger is because you're also getting interest from the 700 bucks the first year. So you're getting interest on the first year's interest, as well as interest on the $10,000. So the amount of interest that you get paid every year is going to be bigger than the year before, isn't it? Real. Yeah, real. And what this derivative is doing is it's telling you how much you're going to pick up starting at year 1, moving to year 2. keep at it. You'll get real good at this. Okay, so there's that. All right, let's take a look at this one. The world population at the beginning of 2000 was about 6.04 billion people. It's been estimated the population is growing exponentially at a rate of 1.6% a year. From everything that you've got there, you have enough information to write the equation for the growth of the population at any point in time. P of t equals. Now remember, we're still following the same pattern. It's an exponential growth. So we're going to use that pattern of P0 e to the r times t. What's P0? 6.04. It's going to be e, what's the rate? Right, 0, 1, 6. And then it's going to be multiplied by t. Another way to write this very same thing is to say, come back, is to say dp, the change in population over time, is 0.016 the population. And what this is telling you is the population is changing at a rate of 1.6% of the population. Do you see that in there? Okay. Either of these two is saying the same thing. The advantage to the form that it's in here on the left is that if you're asked, okay, so what's the population projected to be in 2010? All you got to do is drop 10 in for t, plug it into your calculator, and boom, you're very close to done. Be careful. If it comes out 6.5, it's 6.5 what? People? Billion. Okay, 6.5 billion. Be careful. I've had people on tests with problems like this say, yeah, in 2010 there's going to be 6.5 people. Well, first, I don't want to be a half a person. Okay, and really, only 6.5 in 2010, there's going to be a lot of people disappearing from the planet. I'm going to miss you. No. Okay, that's what everybody's thinking, right? Everybody's going except me. I'm going to make it. Okay. Does this make sense? Are you okay so far? Now, find the rate of change of the population. Ooh. Now remember, is this, just because it's an equation and it has exact numbers and stuff coming out, does that mean that the numbers it's giving us are exact, or are they estimates? They're estimates. You got to be careful. Because is the population growing at exactly 1.6%? And will it always grow at exactly 1.6% each year? No, it's a guess. It's an estimate. So the numbers that come out are hopefully close, but they could be off. Okay, so this says compute the rate of change at the beginning of 2020. How are you going to do that? Okay, we've got our function, P of t, 6.04 e to the 0.016 t. Now that's our function, but is that talking about the rate of change? That's not talking about our rate of change, is it? We need the derivative. So what we need to do is we need to compute the derivative of this, p prime of t, which isn't horrible to do. You know you're going to get the 6.04. You know you're going to get back your e to the 0.016 t. And what are you going to multiply by out front here? Yeah, 0.016. And if you take the 6.04 times 0.016, what you wind up with here is 0.0966. e to the 0.016t, and this is not the function, but this is the derivative. Okay, so you got the derivative. Now what are you going to do with it? Plug in 20. Okay, so to get the estimate, let's see. I was on part C. There it is. So we're going to do the derivative at 20 equals 0.0966 e to the 0.016 times 20, and that's going to give you back some number. Okay, the number it's going to give us back is, aha, look at there. .133. Huh. Okay. 0.133. What's that mean? Billion? Okay. Yep. It is in terms of billions. Billion what? Dollars? People. What about 133 million people? Good. If we started the year 2020, and how big of a step are we going to take? 1. So if we go from 2020 to 2021, it's estimated that the population will grow by 0.133 billion. Probably an easier way to say that to 133 million people. Okay. Does that make sense? And be careful, because part B, which is P evaluated in 20, is 8.3 billion. What's that telling you? That's how many people are expected to have around in 2020. Is that on target, high, or low? It's high. Yeah. Now, one of the things to be aware of when we're doing these derivatives give you a slope, don't they? Remember how a slope fits in on a function. Okay? Let's say we're projecting that the growth is like this. And we're at some point right here, let's say here's 2020, and we're trying to forecast forward. If we do the derivative is going to give us the slope of that line there. True? Look down the road here, and let's say 2025. Our estimate is we're going to be here, but if things are really growing exponentially, where's it really going to be? Above or below our estimate? And our estimate's going to be too big or too little? Too little. Okay, here's something real important to notice. If the function is concave up, that means the second derivative, concave up, is the second derivative positive or negative? Positive. It's smiling. If the second derivative is positive, concave up, the first derivative is going to over or underestimate the true value. It'll underestimate. That's important to know. Okay? If the function is concave down, and here's 2020, and we draw our tangent line, and we're interested in over here at 2025, we're going to be up here, and the true value is going to be there. If it's concave down, our estimate is going to be, okay, the second derivative will be negative. Okay, so if it's concave down, which is what this is, the second derivative is going to be less than 0. So we've got that. But tell me about the estimate compared to the true value. It's going to be too big. It is very important for you to know, is the estimate too big or too little? Okay? Well, what difference does that make anyway? There's a bridge down the road from us. Said 5-ton limit. Clyde and I and Rob run more than 5 tons over that thing. Okay, get a good load of hay going or a truckload of corn. You got way more than 5 tons. We were counting on that estimate of the bridge's capacity being too high or too low? Too low. It underestimated what that bridge could actually support, didn't it? There are times where you want to underestimate the true capacity of the system. An elevator. You're on an elevator, there are 8 people on there, it says 1,200 pound capacity. You're thinking 9 people, geez, we're already over 1,200, unless they're all little first graders. And somebody rolls a piano on, you're thinking, really? I think I want to open this thing. That 1,200 pound capacity, you're hoping that that is way under what it's capable of doing. There are other times where you want to overestimate. Okay? My birthday's coming up. Yahoo! And Becky said, some people want to come over, and I said, that means we have to sit inside. I don't want to be inside. And she said, well, they want to come over and let you know they love you. And I know they love me, but I don't want them to love me inside. Hey, I want to be outside. So I said, I got an idea. How's this sound for a compromise? We'll have a campfire by the pond and we'll roast out hot dogs and beans and make s'mores and stuff like that. And everybody agreed to it. They said, okay, it's Chuck. I guess it's... Now, when I go to pick up fixins for s'mores tonight, should I over or underestimate the amount of chocolate we need for s'mores? Over. What's the problem with underestimating there? They're not going to be happy and Chuck's going to get thrown in the pond or something, right? Okay? So what you need to realize here, is there are times where you want to overestimate, there are times where you want to underestimate, and you must know which your estimate is, because if you've got it going the wrong way, you're in trouble. Does that make sense? Okay, the other type is a limited growth model. These are more realistic. These are more like what you're going to have for the sale of whatever it might be. These are going to be the population of deer in blue ash, the number of catfish in our pond, whatever it might be. The number on top, L, is the limit. This is the maximum you can achieve. Okay? If it's the sales of a DVD for a movie, it's however many of them you made. If it's the number of deer in blue ash, well, it's how many of them can live there. L is going to be an important value. It's typically going to be given to you, so that you have some understanding of the system. Now, where things come into play here, and you got to be careful, is notice L is used twice. It's used up top, but it's also down here in this exponent. Don't overlook that. What you are going to have to compute in every situation is the value for K, right there. And you're going to have to compute the value for C. Oh. So what's going to wind up happening is, oftentimes, you're going to be told, here's the maximum. And it may be something like, we're making 15 million copies of this DVD. Aha, there's the maximum. And they're going to slide it right by you. They're not going to tell you, oh, incidentally, alert, here's the maximum. They're just going to say, we're making this much. And move on. Okay? And you're going to wind up having to compute the other things. Remember, at L over 2, what happens at L over 2? That's where you stop your advertising. Okay? So, there's that. And notice, what is L over 2 on this? What occurs at L over 2? L over 2 is important. L over 2 is right here. This is the inflection point. That's where it changes from being concave up. Do you see the bottom part's concave up? To the top part being concave down. Now here comes a question for you, last one of the day. At this inflection point, what does the value of the second derivative have to equal? It goes from being concave up to being concave down. If it's gone from being positive to being negative, what's it have to pass through to get from positive to negative? It's got to go through 0. So where the second derivative is 0 is your inflection point, L over 2 on this model. Okay? On Monday, we'll dive into some more of these. I'll see if I get some homework problems posted for you in this section. 2.3 is already posted. Folks, I hope you have a fantastic weekend. I'll see you all Monday.